Okay. Can you guys see my screen?
Yep,
Thank
good.
you. Thank you.
Just the desktop, not the actual presentation, by the
I haven't started sharing, so yeah.
way. Okay, cool.
Okay. So yeah, that's where we stopped yesterday, right? So we talked about optical power yesterday. So what happens when we transmit the wavelengths or transmit the lambdas, they all have identical launching power from the same part, right? From one single chassis at one single node. So the power of each lambda is equal or is same, right? So what is the total power of all the lambdas together after being multiplexed? That is what we're trying to find out. So here, as you can see, we can see in the diagram that we're launching two lambdas, P1 and P2. So I'm just going to change the streaming camera so that you can see the board. Okay, should be this one. Yeah, just so yeah. I hope you guys can see the screen here. So what I was trying to say, so suppose there is two lambda, right? So it should be So P1 is one of the lambda and P2 is one of the lambda. And altogether P1 and P2. So what happens when we have a card which has the lambda port, they transmit different lambdas, right? It could be lambda 1, it could be lambda 2, it could be lambda 3, it could be lambda 4. The launch power, the TX power, so all of the lambda, they have the same launch power. They should, suppose here, maybe they will have minus 2 dB launch power, right? So all the lambdas will be having the same power, single lambda, P single. P single means the power of each lambda, right? And when they are multiplexed, so the lambdas, they are multiplexed together, right? And then they are thrown the multiplexer. The multiplexer do the multiplexation and the multiplexer throw the combined signal. So this is P total. This is the P total. So P total, what is the P total power? P total power will be the P single. That means the transmit power of each lambda plus 10 base log n. Here n means the number of lambda. In this diagram, there are 2 lambdas. For this scenario, there will be 4 lambda. You understand what I'm trying to say? Huh? So I hope you guys could see the annotation. So that's the optical power for lambdas or wavelengths in DWDM. People are coming, so I need to let them in as well. Okay, moving forward. Next up, we have the concept of OSNR. So what is OSNR? OSNR is the optical signal to noise ratio. So what is the concept? The concept is that you take a wavelength, you take a lambda, and you see what is the power of the lambda or what is the power of that signal and what is the noise level that signal is facing, and you get a ratio in between them. So OSNR is, as you can see in the diagram, the spectrum is showing different wavelengths. This one is 1530, this one for 1540, this one for 1550, this one for 1560, different wavelengths with different frequency. And here you can see the noise power, the OSNR, right? So it's signal to noise ratio. So the more the noise is increased, the signal will be distorted more, and there will be more interference, and the signal will be degraded more. So a low OSNR means that your signal quality is not that good. Whenever you are running a network, you have to keep a strict eye on the OSNR level of your network. If the OSNR level is going down, that means the condition of your fiber paths or the network health, fiber health, physical health is not that good, and you need to make amend to those situations. Okay. So as you can see, this is a structure of DWDM, very generic structure of DWDM. So where we have the OTU. The OTU means the lambda cards, the wavelength cards, who are actually generating the wavelengths, transmitting the wavelengths or lambdas. And those OTU signals are being multiplexed with the multiplexer or the mark card. Then they are thrown to the optical amplifier. It passes through several optical amplifier and then it reaches the destination. And then we got a demultiplication process. And then with this process, all the wavelengths are decombined or demultiplexed and they are delivered to specific or uh, or they are delivered to their own OTU. So this is how the whole thing is constructed. So if we take a look about the signal power and if we take a look about the noise in the signal, or if you want to understand the OSNR, then things will look like this. So as you can see, the OTU is generating the wavelengths or the lambdas, and the wavelengths are supported throughout the whole path with optical amplifiers. That means they are being amplified. That means the signal power is okay, or they are kept at a proper level. That means if you go ahead, you will see that the power of the wavelength is constant, right? But over time and distance and over passing through different optical amplifiers, noise will be added, right? Because when a signal passes through an amplifier, it adds a little bit of noise. We will discuss about noise in coming slides or in later slides. But for now, just have this idea. Whenever a signal is passed through an amplifier, noise is added with that signal. So as time and distance goes by and signal keeps passing through different optical amplifiers, noise keeps getting added and build up. As a result, the optical signal to noise ratio, OSNR, will start to go down, right? Because OSNR is nothing but a ratio. A ratio means there is a denominator. So at the upper portion there will be the power, at the lower portion there will be the noise. So you divide power with noise. So the result is the ratio of the signal and noise. This is what OSNR is all about. So if we have a very good, or if we have high OSNR, that means our system is doing fine. Our system is healthy. We're not adding up a lot of noises in our network. And the signals which are passing through our network are very good and healthy signals. But if the OSNR is low, that means though the wavelengths have very good optical power at the destination, but the data they are carrying will be error enough. They will be facing degraded quality of data or degraded quality of service at the destination only because of this OSNR. So are we clear between these two? One concept is optical power, another concept is OSNR. Yes, please go
Yeah.
ahead.
Hey, this is Pawan again.
Yeah.
So when you say high OSNR ratio, that means the value, the dividend should be always positive, right? If the dividend goes to
It's a ratio, so it will always be positive. So it's
not should not be a floating or something like,
yeah, something like that. Yeah. So it's a ratio. Say suppose the optical power of a signal is minus 2 dBm or minus 3 dBm, right? And the noise you are having in that signal may be minus 2 dBm. So your OSNR should be straightforward 3 divided by 2. So whatever the result is, that's the OSNR for that lambda in your network. So you need to find out what is the noise level. You need to find out what is the power strength of the signal and to do the manual calculation. But The point is you will always have an NMS, and your NMS is going to help you with this kind of spectrum waveform. So this is a screenshot from one of the vendors NMS, and here you can see that the uh, strength of your signal and the OS signal level, everything is shown here. The value you are seeing here, they are basically showing the OSNR of each and every lambda. So as you can see that it has started from this and it has gone up to this. So it depends what's the value of the noise, what's the value of the signal power, and then you get a ratio in between them. So your NMS will find it out for you. Yes, Mr. Kamal, yes. I cannot hear you.
Right. So my question is, sir, regarding this power of each wavelength, whether it should be mandatorily same or it can be different while
It, it can be different. It can be different. But when you use one type of card, all the TX4 of that card, which belongs or different ports which belong to one single card, they should be or they usually are same. But if you use different types of TX card, then it might be different. But it's okay. You have to make sure that all the TX power of your lambdas are having the same launching power, and your vendor will make sure of it. Because if you do not keep the launching power same, when you do the fine tuning in the amplifiers or boosters, there will be a problem to make all the lambdas same level at the top to maintain a flat surface at the gain level. So that is why we usually what we do, we usually make sure that the TX power of all the lambdas are equal and same from one single station. So that is how not only a station, basically throughout the whole network, we try to maintain that. That is how you will be able to apply different control or amplification methods in the path throughout the whole network. You understand my point?
thank you.
So if you if so 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 just suppose there are five cars, right? They're starting from the same point and they are going to finish at the same point, and in the path they're supposed to use the fuel, right? So if you start all the cars with same velocity, they will reach the station at the same time in the path, and they will be taking same amount of fuel if the cars are identical, right? But if you, each and every car have different velocity at the starting, suppose one has started 60 kilometer per hour, one has started 10 kilometer per hour. So they will be reaching the station in the path at different time, and the requirement of fuel for them will be different, right? But at the station, you have designed one single fuel pump, which can only refill the car at one single rate, right? So the treatment for different rate of velocity for different cars will be impossible at that time. Do you get my point?
Got it, got it.
Yeah. So that is why we want to start with the same power, with the similar power, and then we want to see what kind of extra amplification is needed in the path based on different network topology or requirement or service or function or technology. We use that kind of amplification in the path. So that is why we always try to keep the same launching point. Yes, Shay, yes.
So, like this same power, like for each wavelength. It's only needed if we are using amplifier, right? If they're passive mux, then I think
For DWDM, your lambdas actually realistically have to pass through amplifiers.
okay.
Not cheap amplifiers in DWDM. So that is the main thing. Because whenever you are sending the multiplexed signal from one node to another, in the path, there will be a distance of 40 kilo, 80 kilo, 100 kilo, 120 kilo. And after passing 120 kilos of fiber, when the signal reaches the next station, it becomes really, really weak. So it needs to be
okay.
amplified first. So for amplification, we have two concepts. First, we use pre-amplification and then we use booster. Pre-amplification always works when the signal arrives in the station, and booster always work when we are going to send the signal towards the next station. So what are we doing? We are boosting the signal before sending it in the field, and we are amplifying the signal before receiving it in the next node. I hope that clear your query.
Okay. Yeah. But okay. I have another question also.
Yes.
Like as much as the distance increases, the OSNR will be like affected, right? So for the dispersion compensation, we are also using the fiber pools for negative dispersion, right? So that distance will also increase the SNR, right?
Yeah, it might, but you know what? OSNR doesn't actually fall onto fiber solely, because when you are talking about fiber, you are focusing on the power, optical power. What is OSNR? OSNR is the signal to noise ratio. Fiber is a passive thing. It can hardly add any noise in the signal. So your noise will be added from your active component, like amplifiers. All the amplifiers in the network, each and every one of them will add a little bit of noise in the network. And it is a side effect of using amplifiers in the network. You cannot ignore it. They have to be there. They will be there, right? So you have to design the network in such a way that you are amplifying the signals. Also, you are taking care of the OSNR as well, so that there is a balance in the system. You got my point?
So in such Okay, so in such case, like the dispersion, like the negative dispersion fiber we are adding, it will only add the loss, right? Nothing else.
Yes. So the DCM fiber pole is only adding the distance, length in the network. So with distance and length, you are supposed to face few optical characteristics like non-linearity, like uh, we talked about the characteristics of light, right? Attenuation,
Right.
dispersion, polarization, and non-linearity. There was
Linear.
noise. The light doesn't have any characteristics of noise here, right? So
Okay.
I hope that answers your question. Whenever we're
Yeah, right.
fiber and light, so go back to the slide which we talked about, physics of light. Those things will be affected majorly. And whenever we are talking about worsen, we are basically saying the noise generated by the amplifiers in DWDM. Yes, Mr. Bashar, you raised your hand first. Please go ahead.
Actually, boosters or amplifiers are same.
Boosters and amplifiers, the work activity or the impact is no, not impact. Goal to boost the signal to amplify the signal, but they work for different purpose in different locations. I will show them in later slides. But they basically do the same thing. They try to make the signal more strong. That's it. In simple words. Yes. Yes, Mr. Kamal. Yes.
My question is from the yesterday teaching. This is regarding polarization of light.
Polarization. Yes.
So in that one, our electric field and magnetic field will always be perpendicular even after polarizing the light.
Okay,
Light is moving in z direction.
not necessary, but for the sake of discussion, let's assume that. Okay.
So unpolarized light is also having the electric field and magnetic field
Yeah.
perpendicular to each other.
Yeah.
So what is how to distinguish between these two? Like,
So yeah, so you want to understand the difference between polarized and unpolarized light, right?
yes, yes.
Okay, so the difference is when we consider light as an electromagnetic field, we consider that it has two fields, electric field and magnetic field, right? Are you with me?
Yeah.
Yeah. In that case, the light can flow from any direction to any direction in the open space without any control mechanism, right? Right?
Right.
But in communication channel, do we want that? In communication channel, we want light to follow one direction only, not the all direction. We want light to follow the direction to move forward towards the next station through the fiber, right? We don't want light to go here and there, everywhere. Do we want that?
No.
So what are we doing? For communication purposes, we are polarizing the light. That means we are controlling the electric field and magnetic field in such a way that they follow one single direction, not everywhere. They do not go everywhere.
Exactly.
Is it understood?
Clear, sir, clear. Thank you.
That is why when you go to shops, the eyeglass shops, the optic shops, to change your glass, to change your glasses, they will offer you, sir, this is polarized glass. You can try this one and look at the picture. You will not see the car in the picture. But if you take a look with in blank eye, you will see the car. Have anyone tried taking polarized glass?
Yes, yes.
Yes. So Mr. Bashar, he said yes. So when you tried that, what did the shopkeeper try to prove? So this is polarized glass, right? The shopkeeper gave you a glass and claimed that glass is polarized. And as a proof, he showed a picture that look at this picture, you can see something, you can see an object in the picture. And now try looking at the picture with the glass. You will not be able to see that object in that picture anymore with the glass. Why? Because that glass has been polarized in such a way that the colors consisting in the card is not coming towards your direction. You cannot see the card. So this is how the picture is made, and this is how the glass is made. This is what is happening when we do the polarization. We control the direction of light so that it keeps going towards our specific required direction. Does it make clear, Mr. Kamal?
Yeah. Thank you.
That's the basic concept. Yeah. So as I said, I try to keep it very much generic. I will only talk about the concept. So you go anywhere with any vendor, these concepts apply. Okay. Okay. Moving forward. So now we know about OSNR, and we have seen. Okay, so we have seen what OSNR is. Now there is another thing I need to. Okay. So now we will talk about another concept, optical splitting. So what is optical splitting? Okay. So optical splitting is a way of doing splitting. One signal will be splitted into two. That is the most simplistic explanation of optical splitting. We call the process, or we use this process in case we want to provide optical redundancy to any signal. So maybe you are getting a bit confused. So as you can see in the diagram, we have OLP, optical line protection. So this is a process, or this is a scheme where we provide protection in DWDM. So what is OLP, or optical line protection system? Here, one signal comes into the optical line protection card, or OLP card, and there a splitter is installed. The splitter splits the signal into two different channels. It doesn't change the wavelength, it doesn't change the frequency, it just makes a copy of the primary one. So it splits the signal in two different ways, and it sends the signal over two different paths. And at the receiving end, there is a switch which selects which path to choose to receive the signal. So when the selector selects path A, it keeps getting the signal from path A and receiving from path A. At the same time, the receiver get the signal from path B as well, but since the switch is not pointed towards the path B, it doesn't accept the signal from path B. So as you can see in the diagram, or as you can see here, so this is path A, right? So one signal has come and entered into this OLP. This OLP has splitted the signal into two and send it towards two physical fiber, or two different direction. At the receiver end, there is a switch, right? And this switch selects one path at a time. This splitting happens simultaneously or concurrently. That is why we say it concurrent sending, right? When at the receiving end, this is we call selective receiving. At the receiving end, only one path is selected to receive or accept the signal. When there is a cut in that path, the switch falls to the second path and choose the second path to receive the signal. Is that clear? So that is the idea of optical splitting. Next, we have forward error correction, FEC. This is a very significant and very important idea or characteristic in the DWDM, especially in OTN. So what is forward error correction? Forward error correction is a way to make sure that whatever the transmitting side has transmitted, the receiving side has received it without any error. And if there is an error, the error is corrected by the receiving side. So the idea is to reduce the amount of retransmission by the transmitting side so that the high speed communication can be maintained, time can be saved. So this is and the efficiency and the robustness of the signal can be maintained. So this is the way to make sure that your data is error-free throughout the whole communication process. And there is a limit up to which you can do that. It cannot completely make your whole traffic error-free, but there is a limit up to which it can actually rectify the received signal. So the idea, as you can see, the idea is to encode the traffic or encode the transmitted bytes. So when data is transmitted, it adds a parity, and at the receiving end, it checks the parity. And if there is any error and error is detected, it is being corrected. That is the whole idea of FEC. So now you can say, how is it done, right? So as you can see in this diagram, if we do not use any kind of FEC, so what happens at the transmitting end, 101001110, but at the receiving end, we have received 100. That means this this segment is errored, right? And if there is no FEC, it cannot be corrected. But when we use FEC, what is going to happen? The system or the receiver will be able to detect that this is an error. And then the receiver will be able to make a correction and bring back the actual transmitted bit, which was 1. So this is the process of forward error correction. Now, how this is achieved? So what happens? Okay, let me go to the screen and draw so that you guys can relate. Okay. So what happens at the transmitting end? We are transmitting 00, right? Okay. The transmitting end, we are transmitting 00 or 01 or 11 or 10, right? The transmit side is transmitting this, and the receiver side should also receive this, right? Right? The idea is to create code against this kind of communication. Maybe the code for 00 is this one. Maybe the code for 01 will be this one. Maybe the code for 11 will be this one. Maybe the code for 10 will be this one. Okay. The receiver has the same code in the dictionary. So they both have their own dictionary, and they both have the similar code against similar kind of signal. So if you take a look at the transmit end, so 10, 10, 01, 10, right? So actually the transmit side will be sending 10. So it is 10 110, then 10, same 10110, then 01. 01 means 01100, then it's 10 means 10110. So this is what the transmit side will actually transmit in case of FEC. And the receiving end will be receiving same kind of signal. But if there is an error, things will be changed like this, right? So 10 means 10110, then 00, that means 1, 2, 3, 4, 5. So this is the portion which is changed, right? Then we have 01, that means 01100. We have 1010, that means 10110, 1010. So this is what the receiver end is going to see. Here, it will take a look, it will try to find out what is the difference. So after receiving the 5 bits, this, right? It will see that the next 5 bits are 00000, where the next 5 bits should be this one. So it will make a comparison which should be the accurate one here. So it will try to find out what is the difference. So if we take a look, what is the difference in between? This is the one it has received, right? So if we take a look, how many digits are different in between these two? We can see 2 digits, right? Again, if we compare this, how many digits are different? We can see 3 digits. If we take a look here, how many digits are different? We can see 3 digits. If the number is same between two, then the receiving side will request for a retransmission. But if not, it will try to understand what was the primary signal the transmitting side was trying to send. So it will fall back to the lowest amount of distance and it will try to match that. So this is the working principle. The things didn't add up here only because I was working with some ambiguous number. But when FEC works, it works in this way. I'm switching back the camera. So as I was saying, when FEC works, it works in this way. So the receiving end and the transmitting end, they both have dictionary, they both have codes for the bits and bytes which are passing to them, right? And the codes are similar. So the definition of 00 is similar to 3x and RX side when we are using FEC. In both sides, the definition of 00 is same. For 01, it is same. For 11, it is same. For 10, it is same, right? So when there is a change in bits, so you can ask, how does the receiving side understand that there is a change? It checks the parity. So you see previous slide, parity. So the transmitted data is transmitted with a parity bit, and at the receiving end, there is also a parity check. So by checking the parity, the receiving side understands that there is an error. And what the error could be, then the receiving side goes into detailed lookup and try to match the codes for all the bits or bytes in pair. And if the code matches, like for first one or the third one, fourth one, if the codes are matched, with the transmit byte, it accepts the signal and convert it to the actual data. But if the code doesn't match, it tries to catch up the lowest difference between the received and the supposed to receive code, and it picks this one and fix the uh, received byte. So we will discuss more on FEC in coming slides. So this is just a glimpse. Yes, Mr. Kamal, you have your hands up.
You have answered in the last sentence. You will discuss more in the next slide.
Yeah. No, you can.
Yes, sir, what I was thinking, this parity bit should also change because error is there.
Yeah, that is how.
This example it is not changing. So I was.
That is how the error is detected. If the parity is changed, that is how the receiver and sense that there is an error. And that is
In this slide, sir, parity bit is remains same actually. Transmitting 10 parity bit, receiving 10. So there is no change in the parity bit.
yeah. So this is just an example to
Oh, right.
understand the working principle of APC. So as you can see, we are focusing on the third and fourth bit, right? 10. We are focusing on, as you can see, the blue box. We are focusing here and we are trying to understand if there is an error bit here, how that bit is corrected using the working principle of FPC. That is what we are trying to discuss here. We have discussed the parity one here. So when the parity bit is changed, the receiver already sensed that error is detected. Now it's time to make a correction. And how the correction is made, this is how the correction is made. Does it make sense, Mr. Kamal? Okay, so moving forward. So there are different types of FEC schemes. So different types of FEC have different types of efficiency. The coding gain is basically showing you the efficiency for the coding scheme. So there is on the broader scale, we divide all the FEC scheme in two different categories: hard decision and soft decision, HD and SD. So soft decisions are more advanced now. They are more new approach nowadays. So soft decision FECs are more used nowadays. And there are different FECs like generic FEC or optical FEC or staircase FEC, etc., etc. I'm not going into the details of these. Just I have put this table for your information only. So these FEC, they come with the vendor's transmit card. So whatever the vendor is giving you, they will say what FEC is supported by their card. It is nothing that you can set in your network. Okay, it will be there by default with the presence of your vendor's OTU card. So those cards will be having FEC facilities and they will say which FEC is supported by their card. And in this way, you will understand how much efficient their FEC will be when you run the network. So that is what FEC is all about. So a lot of things on FEC. Moving forward, architecture. So now we understand a lot of things on DWDM. So now it's time we talk about architecture of DWDM, how the whole process is designed, right? It's a very basic diagram and it's a very generic diagram. So whenever you work with a DWDM system, I don't, yeah, okay. whenever you work with the DWDM system, so there will be node A, there will be node B, and in between these two nodes, there will be fiber. That is the very basic structure. And if you expand your view, you will see that the fiber length is very, very long. So you also needed to place some small station in the part where the signal was just only amplified, nothing else. You did no add up signal, you did no dropout signal, you just amplified the signal in the path in some node. So that's one thing. And to amplify the signals, we use amplifiers or boosters, whatever it is, depending on the side of the transmission or receiving. And if we take a look at the station, the transmitting station or the receiving station, there will be few specific tasks each station is doing. For transmitting station or receiving station, there will be client facing card, there will be line facing card, and there will be amplifiers, there will be boosters, there will be multiplexer and demultiplexer in that station. So as you can see in the diagram, we are showing DWDM system connected over fiber. In the fiber path, we have DCM, we have EDFA, and we have VOA, or the amplifiers. And EDFA are also amplifiers. VOA is variable attenuators, which can be placed physically, and DCM is dispersion compensation modules we use to compensate dispersion in the path. And when the signal enters or leaves a station, the leaving station is the transmitting station, the entering station is the receiving station. So at any station, there will be multiplexer, there will be demultiplexer, and after doing multiplex or demultiplex of the system, those signals will go into the line cards, and that line card will actually convert the wavelength from color lambda to gray lambda, so that the signal or the payload can be delivered to the client in gray lambda or 1310 or 1550 nanometer range. So when we talk about a generic DWDM system, this is what it all looks like. Now it can be any vendor. They can have different names for different functionality of cards. So vendor A can name their OTU card as A, vendor B can name their OTU card as B, but basically both the cards are doing the same thing. The OTU cards are converting the lambda from color to gray and gray to color. That's the task of the OTU card. They transmit the wavelength, they transmit the lambda. That's the function of the OTU card. Now, it doesn't matter which vendor calls their card in which name, they should have FEC, they should have specific or range of lambda supported by them. They should have specific transmit power for lambdas. They should have similar kind of data sheet with different figures, varies from vendor to vendor. So one might have support SDFEC, one might have support HDFEC, one might have support advanced SDFEC. So, but they all should support FEC. They all must support FEC, because without FEC, OTN or DWDM nowadays is unthinkable, right? So this is kind of making it generic that whatever the vendor is doesn't matter. The concept will be similar. Okay. So what we will do now, we will try to magnify into the whole system, and we will try to discuss each component one by one so that we understand completely what the whole architecture is trying to tell or trying to do altogether. Okay. Okay. So first, if we take a look, we have transponders. Transponders have two sides, client side and line side. As I said, the line side is towards the network side, towards the multiplexing side. It is colored, it has a specific lambda, and it will be unique in the system. But the client side will be gray as it is shown in the picture, and it will either be 1310, or if you use multi-mode cable to connect in the same DC or in the same shelf, you can use the 850 as well. Next, we have amplifiers. Amplifiers can be EDBM doped amplifiers or EDFA. Amplifiers can be Raman amplifiers. So these two kind of amplifiers can be used. We will discuss each and every one of them gradually. Okay. Next, we have add drop filter or max demax unit. So these add drop or max demax units, they have the band of whole wavelength range which this system is capable of serving, right? The whole C band or the L band or the odd C band or the even C band. It can be different, the version can be different, the look can be different, the variation can be different, but it is what it is. It is a card which will carry all the wavelengths. Now, the multiplexer and the demultiplexer, they both are same. The only difference is multiplexer will multiplex the signals, demultiplexer will demultiplex the signals, but their loop or their lambda will be same. The list of channels they support will be same in one single system. It cannot be different. Next, we have dispersion compensation module or DCM. Yes, Mr. Kamal, you want to say something?
Sir, in transponder, how many input can be provisioned in one transponder?
Good question. So as I said, the transponder is different from vendor to vendor. So some vendor has one port transponder, some vendor has two port transponder, some has four port transponder. Four port means one card is able to generate four different lambda. Okay. One port means one card is able to generate only one single lambda. So these OTU card or these transponders, so there is two concepts, transponder and max ponder. This is more related towards the arrangement between the line and client side, but as a general naming, we call them OTU card. So the OTU card, they can be having one port or two port or four port or whatever the vendor have designed it to have. So it differs. It doesn't have any universal rule. I hope that answered your query.
Yes.
Yeah. So these are the components you can see here. So the components involve the OTU card, it involves the max demax unit, it involves the amplifiers, it involves the dispersion compensation module as well. The one thing which is not shown in the picture is the management channel. So as you can see, all these signals are being multiplexed and transmitted in the fiber, right? And at the receiving end, the demultiplex has received the combined signal and doing the demultiplexing, right? But there is one channel which is sent alongside of this multiplex signal. This signal is used for doing all kind of management in the system. We call them OSC, optical supervisory channel. So OSC is responsible to carry out all the management and all the control communication related activities in the whole network for all the nodes. And OSC is calculated from one node to another, point to point. So it cannot be point to multi-point. It cannot pass through any optical line amplifier, because if there is an optical line amplifier, the OSC has to be dropped there, and then it has to be regenerated from there again towards the next direction. So this is how the OSC works. We will have discussion on OSC in later slides. I'm just telling it you right now, since the OSC demarcation is not here in this picture. So I'm just telling you so that you guys don't miss it. So apart from what you're seeing in this picture, there is another component which we call OSC, and which is used for all kind of communication, all kind of management for all the nodes in the system. Moving forward, so first thing we would like to discuss is the OTU cards, or as we said, the transponder or muxponder. As you can see in this diagram, the elliptical red shape, this segment is called the OTU segment. Here, the lambda conversion or color conversion is happening. At the same time, client is onboarding and delivering, and at the same time, line is onboarding and delivering. So this is the task of OTU section or OTU cards. So they can be transponder, they can be muxponder. So what is a transponder and what is a muxponder? So both the cards, both the transponder and muxponder, both of them has similar multiplex, has similar uh, uh, colored output, not multiplex, colored output. Both the muxponder and transponder, they both have colored output. But when we onboard client, the transponder carries the client, which is the capacity of the wavelength in total. So here in this transponder, you can see the wavelength has a capacity of 10 gig, right? So the client will also be connected from a 10 gig Ethernet port. But in muxponder, the wavelength is still 10G, but the client is connected in different granularity. Here it is connected in 1 gigabit Ethernet port. Here it is connected in STM16. Here it is connected in 2 gigabit fiber channel. Here it is connected in STM4. Here it is connected in a 1 gigabit Ethernet port again. So the combination of different client port from different kind of payloads, they all together be mapped into the capacity of the line wavelength. But for transponder, it will be one in, one out. For muxponder, it will be many in, one out. What is the out? The out is the colored lambda, and that lambda has a specific capacity. It might be 10G, it might be 100G, it might be 200G, it might be anything based on your system and design and card and whatever you are using. But at the receiving end, if it is a transponder, the capacity of the line or line side or the wavelength will match the capacity of the client side, one in and one out. But if it is a Mach responder, the capacity of the line side will also be matched to the cumulative capacity of the client side. Altogether, they will match this capacity, but they might be different in separately. So it will be many in and one out. So that is the difference between Mach responder and transponder. Moving forward, next we have the multiplexer and demultiplexer. So as you can see in the diagram, after client is connected, then the wavelength is converted to color, and then the OTU cards are connected to the Mach and Demach units. So if we take a look at the Mach and Demach unit, so what it is doing, so the Mach unit is multiplexing all the colored lambda, as you can see, the colored wavelengths. The Mach side or the multiplexer is doing the multiplexing, and the demultiplexer is doing the demultiplexing. It's receiving the combined signal here, and it is doing the demultiplexing of all the color lambda. So if you compare this operation, you will see the operation matches with the working principle of Prism. So in Prism, we see that if there is a white light, and if the white light is incidenting on one side of the prism, the other side of the prism will actually give you different colored light. So this is the very basic principle of doing multiplexing and demultiplexing. So in multiplexing and demultiplexing, similar kind of prism, small prism is installed, and they actually do the operation like this in this very basic concept. Okay. Yeah, I can see your hand, Mr. Kamal.
Sir, in this case, output of OTU card can have the same wavelength to OTU card. The same color output, say green.
So I understand your question. So you are asking if two different OTU card or two different OTU port can have the same wavelength or not, right?
Yes.
So if you go back to this diagram, if the OTU card have same wavelength, so suppose this is OTU1 and this is OTU2, right? Oops. I should really stop using. Okay. So suppose this is OTU1 and this is OTU2. So if they have the same wavelength or same colored lambda, then at the Mach port or at the Demach port, which one will you connect? Because the Mach or Demach card has one single port for each and every unique lambda. So there is no repetition there. Understand what am I trying to say?
So Mux card is designed in such a way that it will not be have its same lambda.
It cannot be repeated. It cannot be repeated if you use a lambda in one direction. So altogether, these Mach and Demach unit, they are actually representing a direction, right?
Yes.
So once you configure a wavelength or a lambda towards one direction, you cannot repeat that lambda in DWDM system. If you could, then we wouldn't have needed lot of bands. We wouldn't have needed the whole C band. We wouldn't have needed the whole L band and moreover U band. So why do we need these bands? Because you cannot repeat wavelength. You just can't. For now, take this statement, you cannot repeat wavelength. You can repeat wavelength in such a way that you have to make sure the repeated wavelength from one point to another is not going to see each other in the network. Do you understand what I'm trying to say?
Understood.
Maybe I'll explain a bit. So you have a huge network here. Maybe I'm going to draw something. So suppose you have a huge network here, okay? So you have one node here, you have one node here, and maybe there is a bunch node, okay, from this part. So you have provisioned lambda 1 through here, and maybe the protection path is through here. So you cannot again send lambda 1 from this node to this there. But what you can do, for only this portion, you can use lambda 1 here again. But this lambda will be confined to this segment only. It will not interact or it will not go in these paths. Is that clear?
Thank you.
So that is the idea of repeating lambda. You cannot basically repeat lambda in DWDM system. That is the main concept. But for some exceptional requirement in some exceptional design, you can actually do that if you are running out of wavelength or lambdas. Moving ahead, so we have discussed the multiplex and the multiplex units. Next up, we have the EDFA or the amplifiers. So what is the idea? How the amplification is done? So when the light comes into an amplifier, we use a laser pump to pump lasers, and three states are there. So it's basic state, it's metastable state, and it's high energy state, right? So when we pump the lasers go to the high energy or excited state, and then after passing some time, it decays energy and it comes to metastable state. And then in that metastable state, these pumped energized lasers are combined with the incoming signal. Thus, the incoming signal also get excited or amplified or uh, uh, get the strength with the help from these excited photons. So this is how the amplification basically works. This is the concept. So there are some components in EDFA or EDBM doped fiber amplifiers. It involves the iridium doped fiber, the laser pump, the WDM coupler, the optical isolators, the gain flattening filters, and noise figure. So when we use optical amplifier in the DWDM system, the signal has to go through all these components one by one. So the fiber, EBM doped fiber, this fiber is used in the optical amplifier to support the photons to be pumped and get excited in energy, high energy level, that is E3. Then pump laser, the laser pump is used to pump the lasers. Then the WDM coupler is used to combine the excited lasers along with the incoming weak signals. They mix together and they becomes in the metastable state E2, and that is how the excited photons, they lose some energy, the weak signals, they gain some energy. So that is how the weak signals are amplified or boosted. So we make sure that after doing the amplification, all the wavelengths have a similar output. As you can see in this diagram, the P out, all the lambdas are amplified and they have the same flat gain at the top. When the lambdas came or wavelengths came into the amplifier in P in, you can see the amplitude of the signals were very low. And after passing through the EDFA, after being energized by the laser pump and being energized and being coupled by the coupler, the weak signal becomes strong and amplified. So this is the working principle or concept of optical amplifier. Uh, what are the advantages? So it involves getting high gain and low noise, but noise will be there. Whenever you pass the signal through any kind of amplifier, there will be noise added with your signal. That's for sure. So the noise will be there, but for EDFA, the noise level is not that much. And for EDFA, your vendor will tell you what version of amplifier they are giving you and what is the noise factor for that amplifier card. So if you are having a DWDM network and if you are using optical amplifiers and if you do not know about the ASC noise or noise factor for that amplifier, you can talk to your vendor or you can look into the data sheet of your product to find it out. And what are the applications? The applications basically focus on extending the strength of the signal and make sure it reaches a long a long distance from source to destination. It can be used in DWDM or it can be used as different forms like amplifier or inline or booster. So somebody was asking if what is the difference between booster and amplifier. So the working principle are same. They are both based on the goal to amplify the signal. It depends where you are using it. If you using the amplification before sending the signal at the transmission side, it will be a booster. If you use the amplification before receiving the signal at the receiving side, it will be a optical amplifier or preamplifier. Yes, I can see a hand. Yes.
Hey, hi. So now, if you go back to the previous slide, these particles are energized with a laser being pumped on them, right?
Yeah.
So, do you think like there isn't some expiry for these I mean ions to be energized? Like they, I mean, is there a validity to use amplifier in the system? There is a time frame, like is there a time frame so that this for I can use an amplifier in the system for 2 years? After that, it won't be operational.
You mean the life or longevity of an amplifier?
Amplifier? Yeah, yeah.
Okay. So you understand why we are using amplifiers, right?
Right. Yeah.
So can you tell me why are we using it?
Yeah. I basically to amplify our existing signal which is coming into the system, right?
Yeah.
But since these are the ions which are actually energizing the light coming in, these ions will not be
Okay.
will have to go.
So I got your question. Okay. So that is why you need to take a look at the second slide which I was discussing. There is a laser pump. Okay.
Okay.
So this is an active pump which basically pump laser in instant.
The ions to go to a higher state.
Yes. So it keeps pumping the laser as long as it keeps getting the power from the device. You get my point?
Got it. Got it. So it's a cyclic process, like laser will.
Process. It keeps happening all the time. So there is no expiry date on the ions because yeah, there might be expiry date on the ions because the excited ions are gonna get weak over the time and over distance. But the pump laser is using electric power to do its work and produce the ions and pump the lasers into the iridium doped fiber. So that is how new lasers are always there to excite the signals which are coming as weak into an EDFA. You get my point?
Got it. Yeah.
Cool. Yes, Mr. Kamo.
Sir, this laser pump should have the same wavelength as that of the signal.
No, of course not. If it has the same wavelength, then there will be a collision of wavelength, right? Because at the receiving end is receiving the wavelength in C band. So what it is doing, it is using the wavelength from 980 nanometer to 1480 nanometer. So these are the wavelengths which has the photons or which has the light photons which can be excited to E3 and can be maintained a meta-stable state to E2. So you can ask why why it is like that. We are using this wavelength different, right? You can ask that the pump light is 980 nanometer and the incoming light is from C band, right? So they are different. Why? They are different because we are, first of all, we are trying to pump lasers. So 980, that means we are using the laser or wavelengths for multi-mode supported version, right? So you can pump a lot of lasers. They are going to E3 and then after decaying some power, not in terms of radiation, but in terms of temperature, they come to a metastable state, which is E2. And the wavelength in this window are the most efficient wavelength to be used in this principle from E3 to E2. That is why we use this window for pumping lasers. I hope that answers your query.
Thank you, sir, but still not very clear.
Not very clear. Okay, see, the thing is that we have only 3 days to cover, and I will not be able to make all the concepts crystal clear. What I'm trying to do, I'm trying to give you guys a push and give you guys at least a level of clarity as much as possible I can, so that you can go back to your workplace or to your life and you can basically dig down more, and you will be able to understand as you study more on these things once you have the basics. So I'm just trying to fix that basic, if that make any sense to you guys. Yes, Shai.
Oh, so my question was about the last slide, the transporter one. Can I
Yeah,
ask?
yeah,
So,
sure.
so we are using like transporter for converting gray optics to color optics, right?
Here, are we
Okay.
talking
So if
now?
yeah, this one. So if the end equipment directly support color optics,
Hmm.
can we avoid transporter at all?
Yes, if the end
Okay.
device if the end device or client device support color recipe, you can connect that signal directly towards your multiplexing or demultiplexing unit. Here,
Okay. Okay.
in
Okay.
that
Thank you.
case, you will not be used. But you have to make sure that the loss or the TX power which is needed for the system
Ah,
is maintained by that client device is color recipe. Are you getting
okay.
the point? So
Yeah. Yeah. I got it.
maybe in your DWDM system, you have OTU cards who has a launching power of minus 2 dB. And now you are connecting with a client. That client has a colored SFP in its own router, and that colored SFP is throwing a specific lambda, maybe lambda 8,
Mhm.
and it has a launching power of minus 4, which will be very weak compared to your system because your system has minus 2 launching power. Your whole network is designed based on the fact that your lambdas are being launched with this much of power. Now, if you add any other lambda with a different launching power, the performance of this lambda in the path will be different compared to the other lambda you have in your system, because all the parameters in the amplifiers or EDF or whatever you can see, all the parameters are designed based on the fact that the launching power is minus 2. Maybe in the EDFA you have applied 12 dB gain, and this 12 dB has come from a detailed calculation where the TX launch power for OTU is minus 2. Now, if you connect something with minus 4, here it will pass through the same EDFA with 12 gain. So at the receiving end, it will be showing a weaker signal compared to your own native lambdas. Are you getting my point?
Got it. Got it. Yeah, yeah, it makes sense. Actually, I asked the question because I've seen some transport networks where they are not using transporters at all. They are using gray optics directly in the networking gear.
No, no, they are not using gray optics. They are using colored optics.
Color optics directly in the networking gear.
Yeah, they can.
And
There are
okay,
solutions.
also I have one more question.
Yes.
So, like DWDM, the whole concept of DWDM is to like use multiple wavelengths over a single channel, right? But let's say we don't need multiple wavelengths, we need only single wavelength, but for larger distance. So we can still use DWDM, but the mux will be not useful, right?
So you need only one single wavelength, but
Yeah,
you need to carry the wavelength to a long distance.
yeah, yeah. Right.
Yeah, definitely you can. There are,
Because that also I've seen in some transport networks where
yes,
they used all the installed all the systems, but they are using only single or like two wavelengths, just like that.
yes, you can. You can.
Okay, okay.
You
Thank
can.
you.
So you know what? It's so basically at the end it comes down to the finance. Okay. So how many lambda you are going to provision? What is the revenue from that lambda you are going to generate or you are going to earn, and what is the cost of the solution you are going to provide for that lambda? It all comes together to make a decision whether you can do it or not. But if you talk to me in pure technical aspect, yes, you can do that. But if you talk to me in practical aspect, I would say you need to take a look at a lot of factors before doing that. I hope that answers.
Okay, okay. Yeah.
Yes, yes, Mr. Kamal.
Sir, this is regarding multi-mode and single-mode fiber.
Mhm.
So capacity-wise, multi-mode is better because you have multiple wavelength, multiple paths
Yeah,
from one point to other point. But still, we prefer single mode because of attenuation, as you said earlier.
yeah.
So why not we are going with the multi-mode rather than single mode?
So we are not going with the multimode because multimode fibers cannot actually take your signal to tens of kilometers or 20 kilometers or more than or any other bigger value. If you use multimode fiber, you will be needing to use uh, a regenerator node after every 2 kilo or 3 kilo or something like that. So to carry 100 gig of traffic uh, from point A to point B, if there is 100 kilo of distance between them, you need to place at least 50 stations in between, which will basically again kill the strength of the lambda, and it will not be able to survive because of being involved with too many amplifiers in the path and being added too many noises. So it is not practical to use multimode fiber, and that is why we cannot use multimode fiber for DWDM. We need to use only single mode fiber. Does it make sense?
Yeah, sir, I got it. So in single mode, as you said, 96 channel can be multiplex.
No, not necessarily only that.
Maybe
It can be anything. So how many channels are being multiplexed or demultiplexed? It depends on your system design. It doesn't actually directly depends on the fiber type. You got my point?
in the last study you said, no, sir, in the single mode fiber, we can have at the most 96 plus channel.
Not at the most. We generally have 96 channels in a DWM system, but we can use ultra long band as well. We can use L band as well. There we can double or triple our wavelengths as well. So the wavelengths can be increased. It basically doesn't depend on the fiber type, but for single mode, we basically use the system in plain without any kind of extra type of modification. We usually use a 80 channel or 96 channel system. And then if we run out of that wavelengths, that is meaning that we have run out of C band, then we extend to L band and then U band, and this is how it happens. But there is no limitation of the wavelength depending on the fiber type in single mode. So that doesn't actually, that is actually not what I said. If you understood it that way, then correct it. So how many channels is going to be used? It depends on your system design. It depends on your network architecture. It not actually completely depends on fiber. So yeah,
Thank you. Thank you.
you will understand about this question more as I go ahead with uh, my coming slides. You will get more clarity on this. Okay, just bear with me. Okay, so moving back where we were, we have completed EDFA. Then we have another type of amplifier, which is called a Raman amplifier. So if we go back to EDFA, EDFA happens in an active card. It is a card in the shelf, and the amplification is happening inside the card. The boosting the amplification, the EDFA process, and the output of the card is a high gain signal, right? But if we talk about a Raman amplifiers uses the characteristics of optics or light to amplify the signal. So we have gone through the concept of non-linearity, right? So what is non-linearity character of light? Can anybody tell me? I would be happy to listen. Any volunteer? We discussed this on the first day yesterday. So yes, please.
Yeah. So light generally tries to lose its energy as it travels through the medium. So the signal strength, whatever is at the source, is not necessary. You'll have the same signal strength at the destination. So I mean, it loses its energy as the path goes,
Uh,
as the path.
not not quite there.
Response of material to the light is not directly proportional to the light intensity.
Yes,
Into complex some behavior, what you said.
yes, it is about the intensity of the source. Yeah, yeah, perfectly said. So the non-linearity effect is about the intensity of the source of light. So the light coming in very strong in the medium, and that is why non-linearity effect happens. And when it happens, we can see different type of symptoms at the output. We could see a different wavelength which were transmitted. They're not matching with the received wavelength. We can see amplified wavelength which was transmitted. Now we are at the output, we are seeing very strong signal as well. We can see some different other symptoms as well. So Raman amplifier or Raman scattering, stimulated Raman scattering, this whole process uses that concept. So what it does, it throw a very high power laser pump into the optical fiber. And the wavelength of that pump is lower than the signal. So the energy of that laser pump excites the vibrations in the silica fibers molecules. And that is how the path helps the signal to get amplified. So in Raman amplifier, amplification of the signal happens throughout the whole path from A to B in the fiber. And it is being done with the help of the high pump, high power laser pump at the source. So that is how this Raman amplifier works. So this Raman amplifier basically works in the whole path. So the path is basically helping the signal to get amplified. And also because of the path, the signal is getting weaker, but only because of the high power pump at the source, the path is also aiding power or strength to that weak signal. And throughout the whole path, it is being done until the signal reaches the destination. So this is the whole concept of Raman amplifier. Raman amplifier is very much expensive, and basically it reduces the not reduces it reduces the noise, and it improves the signal noise ratio as well. So Raman amplifiers, for Raman, using Raman amplifiers, you need to have special kind of patch cords as well because of the high laser pump at the source. So if you do not use special patch cords, your patch cords are going to get burned every now and then. So that is one thing you need to take care of. It can be backward pumping, it can be forward pumping. So the backward pumping means the laser are pumping from one point to another, and the pumping is working on the opposite direction of the laser. The forward pumping means the pumping is working with with the signal toward the same direction. So when the pumping is happening with the same direction, I mean, when we are using forward pumping, we are basically offering higher gain efficiency. But when we are doing backward pumping, we are basically offering better noise performance for the signal. So that is what Raman amplifier is all about. So at the same time, both forward and backward pumping takes place. So the forward pumping gives gain to the amplitude of the signal. The backward pumping gives better noise performance so that the OSNR through the whole path remains intact and improves over time, not degrades. So that is the whole working principle in short for Raman amplifier. Advantages. So what are the advantages? It has a broad wavelength amplification, reduces signal degradation for application. We use it for long haul or ultra long haul. Raman amplifier basically can be seen in subsea networks as well, where you use the amplification in the fiber underground the sea. So it's a long distance and it's very difficult to use active stations. So that is how basically we aim to improve the signal power. So what amplifiers basically do? So when we talk about conventional optical transmission, we talk about one node to another. Yes, Mr. Satish, you have a question?
Yes, we have discussed about Raman amplifier. So in conventional amplifier, there is a signal get again signal required again amplification after 80 or 120 kilometers. But what is range of Raman amplifier when it required re-amplification?
So the Raman amplifier, I do not recall the exact specifics of a distance for Raman amplifier, but it is much larger, much greater than EDFA, because EDFA happens in an active card. So you can only reach out to the next hop, and after that you need to use the EDFA again. But when you use Raman amplifier, it is happening within the fiber itself. So if it is a 120 kilo or 180 kilo fiber, the whole fiber works as an amplifier for the signal because of the SRS effect, Raman scattered Raman stimulated Raman scattering effect. So why my hand is showing up? So yeah. So that I will get back to you after the break with specific links supported by Raman if I find the information. But right now I don't have it with me. Yes, Mr. Vino.
Okay, no issue. Thanks.
Thank you. Mr. Vinod, you wants to say something?
Hi. So this is like a typical doubt. So yeah, we are using amplifiers, but my question is, if we can increase up power of in the initial stage itself, like, but there should be a limit, right? What happens when we amplify so much so that we can reduce the number of amplifiers in between? Is there a physical limit how much we can amplify at the initial stage?
You mean the TX launch power?
Yeah. TX launch power. So if we can increase up to its limit, what happens to the card, or what is the physical limitation which is constraining so that we can't amplify so much, so that we can cut off all the amplifiers in between to reduce the cost?
I got your question. So see, the limit for transmitting a wavelength is actually defined by the OTU card you are using. And the transmit power is different from vendor to vendor, and it is also different in a same vendor from card to card. So the transmit power for 100 gig lambda will be a bit different than the transmit power of 10 gig lambda. Again, the transmit power of 10 gig lambda of vendor A will be different from the transmitting power of 10 gig lambda of vendor B. Now, point number one is it can be different. It will be different. Point number two, how much can we increase the transmit power? Is there a limit? Of course, there is a limit, because if you make the source really, really strong, you are going to face the effect of non-linearity in the path. So that is why in the beginning we have discussed about these optical characteristics. So we just discussed about it again few moments ago. So what is non-linearity? This is an effect, or this is some unwanted behavior of light waves, which occurs when the source has a very high intensity light or optical power. That is why we basically cannot go as much as we want higher in the TX launch power. It has to be within a very defined range, and that range is designed by the hardware architecture or by the system architecture of that vendor. Second, how
Okay,
much? Yeah. Second, how much amplifiers we can use, or is there a physical limit for using number of amplifiers? So the number of amplifiers you can use will be limited by your OSNR. If you use too much amplifiers in the path, your OSNR will be degraded, because each of the amplifiers will introduce noise in the system, and because of that, your OSNR will go down, and at the receiving end, your signal will be strong but will carry garbage data, because the service is already degraded. You get my point? So,
yeah, okay, thank you.
so I hope that answered your query. Thank you. So I think we are due for a break. It's three. Okay, after 5 minutes we will go to the break. Okay, at 3:30. So as you can see in the slide, for conventional optical transmission, what was happening? We used repeater. We used end stations from one station to another. We had to carry the signal by doing a repetition of the signal again and again and again. For WDM, we use optical amplifier. That means we do not have to regenerate the signal. We do not have to use repeater. We can use the same signal and we can boost it. We can put gain on it, and we can amplify the signal, and we can pass it forward to the next destination. So this is the difference amplifiers make in your system. Using repeater in the path is way, way more costlier than using amplifier. So we would definitely want to reduce our cost when we design our network, because we are going to reduce the number of fiber, we are going to reduce the number of cars, we are going to reduce the number of complexity in our network by using optical amplifier. So it is a must that in DWDM system, you have to use optical amplifier. But how many are you going to use? That depends on the planning stage by the planning tool. This will be designed by your vendor with the help of their planning software. But again, you can also calculate it. You can also have understanding of it by yourself doing math from the paper as well. When we will talk about the calculation of optical power tomorrow or later in the evening today, you will be able to see how you can understand that. Yes, Mr. Shatis.
Yes, regarding the current discussion, so is there any signal noise ratio range? What is ideal one, and up to what level we can design our system which can work to deliver our network requirement? Is there any particular range of this OSNR?
Yes. So the OSNR, which is so the OSNR range will be showed to you by your vendor before implementing the network, and these OSNRs will be coming from their simulation tool. Suppose you have a network and that network is present in 10 cities in your country. You have the DWDM locations in 10 cities of your country, right? Or in 20 cities of your country. And it is connected with each other with different topology, and you are running maybe 40 lambda all over the whole network. Your vendor, before provisioning the whole network, your vendor will give you a Lambda report where they will share what are the wavelengths they are using and where are they using those wavelengths, from which node to which node, and how many capacity they are carrying, what are the modulation technique they're using. And after running the network in a simulator using the loss you have provided them for the fibers, using the loss data, using the number of wavelengths, using the system architecture which they have designed for you, putting all those in the simulator. They run the simulator and they will show you what is the OSNR for each and every lambda you will have after you run the network. There you will get a visible idea what OSNR is going to be there for each and every lambda. The OSNR, you want to keep it as much as possible, because your lambda card will say that the which lambda should have what kind of OSNR. So your lambda card will have the threshold in itself. If the threshold is crossed, your lambda card will generate alarm in the NMS. So the threshold you're talking about, the threshold will basically lie into your OTU card. So your OTU card will be giving you the exact threshold in which your OSNR should be there in real life. But again, when the vendor do the simulation, they will show you the OSNR that will be there after running the network. And at the same time, they will also tell you what is the required OSNR to run it successfully. If you ask them, they will provide that data to you as well. I hope that answers your question, Satish.
Yes, thank you. So there are multiple factors based on requirement. They can modify and plan accordingly. Thank you.
Because the OSNR, as you know, the signal to noise ratio, the power of the signal, and the amount of noise. Now, if a lambda has to cross 15 amplifiers, it will have an amount of noise. If another lambda has to cross 40 amplifiers, it will have another amount of noise. You're getting what I'm trying to say?
Yes, exactly.
Will vary on the lambda on your design, how a lambda is propagating from which point to which point, how many amplifiers it is passing through to reach its destination, what is the wavelength of this lambda, what is the capacity, what is the modulation it is using. Based on all those factors, the OSNR will be there, and everything will be calculated by the simulation software. If the vendor doesn't give you that, you can definitely ask them to give you that or share that with you, so that you can understand before deploying the network. You can understand that if you design this network, if you take this network from that vendor, how much strength you have in your hand. I mean, how strong the OSNR you are going to have in your lambda. If you see in the simulation report that the levels are not good enough, you can ask your vendor to redesign. You can ask them to reduce the number of amplifiers in the path, and you can have more discussion with your vendor or with your transmission planning team internally as well. Not everything depends on the vendor. You also need to work on your part as well. So yeah, it's a cumulative process. I hope I could give you a glimpse of idea what it is all about, Satish.
Yes, exactly. Thank you.
Okay, I think we're due for a break, so I'll stop sharing now, and I'll pause the recording.